No, I mean, I'm pleasing this gentleman over there. This is quite a light that you're shining on me. What's this light for?
This is a projector for.
Okay. So, tell me, give me the sign. Okay, ladies and gentlemen, it's my pleasure to introduce Pascale Fung, who is a graduate of all sorts of places, but has PhDs from Columbia University under Kathleen McEwen, and she's now at the Hong Kong University of Science and Technology. She was participating in the 2000 workshop, and is a famous person all around. Go, Pascale.
So, good afternoon, everyone. I'm really happy to be here again. After a year and a half this time, see some old friends and some new friends. So there are a lot of projects going on in our center, and today I'm going to focus on talking about 3 topics that are related to speech translation. Am I loud enough? Yeah, okay. So the focus will be on how we reduce confusions on the speech side and ambiguities on the on the text side for speech translation. As it's well known, speech translation is slightly different from open domain, large domain machine translation, in that the applications of speech translation are often peculiar, in the sense that we are often only interested in extracting the what, who, when, and where, why containing the speech input. It's usually a query, asking for direction, booking hotels, and these kind of things. So the challenges in speech translation, in our view, there are 3 main challenges I'm going to cover today. One is the spontaneous speech. In speech translation, people are going to be talking spontaneously and often with accented speech. And this is a particular important problem for Mandarin speech, because most Mandarin speakers are non-native speakers. And secondly, I will talk about extracting named entities, which encapsulate the semantics of what, who, when, where, a lot of this, from voice data. And third challenge, of course, is the solving the ambiguities in translation candidates. For every word, source word, there are multiple translations in the target word. That's the eternal problem we have to deal with in machine translation. In speech translation, we might not be generating grammatically correct target sentences, but we definitely need to translate the source sentences, the words in the source sentences, into the correct sense. So our strategy or the topic today is really focusing on reducing the confusions in the speech and the ambiguities in translation in order to improve speech translation. So here are 2 popular, I would say, paradigms for speech translation today. One is the noisy channel model, I think all of you are familiar with, and the other is the interlingua model. Noisy channel model of speech translation basically combines automatic speech recognition with statistical machine translation. And this is a challenging task, and today a lot of, the latest trend in research in speech translation is open domain speech translation. So you've got open domain recognition, open domain SMT. Now, another very important paradigm people don't like to refer to is actually interlingua. Interlingua sort of fell out of favor a while back when SMT became popular, but in fact, many of the practical speech translation systems today are based on interlingua and not on this paradigm. So interlingua is the system, is the paradigm where you actually have an understanding module of decoding text into some kind of a semantic form, and usually the semantic form is referred to as interlingua. Other times it's just called semantic structure. And then there's a generation module which will generate the target sentence. And very often in speech translation, we take the interlingua directly and we do something. For example, we fulfill a request from the user. We give some information. So this is not necessarily a generation module for speech translation here. So for both these paradigms, the 3 challenges I mentioned remain. For example, here, Named entity recognition, of course, a very important part of interlingua, automatic interlingua generation. Translation disambiguation is important for both types of systems. And accent modeling is very important if we want to recognize spontaneous Mandarin speech. So I'm talking about when the input speech is in Mandarin and the output is either a semantic structure or English sentences, or if you want some other languages. But the input is Chinese, so the accent modeling is important. So let me first talk about named entity recognition from voice data, from Chinese voice data. So I don't know, anybody needs introduction to named entities, but here you have a complete sentence, and then the words in red have been bracketed and labeled with person, location, person, organization. And this is named entity recognition. For example, Wolf is recognized as a person, Argentina as a location, Del Bosque as a person, and more importantly, Real Madrid. Real Madrid is identified as an organization, not a location. And this is important. So how can we do this automatically? And more importantly, we want to do this in Chinese, and secondly, we want to do this from speech recognition output, which has errors in them. So NER is basically, we need to first find the boundaries of this. These are the named entities, and then we have to label them by their type. For speech translation, having a good NER system, of course, helps helps the speech translation task. In particular, we also know that named entities do not usually translate literally between languages. Right? So if you translate this as the real Madrid, as in the real veritable one, then we'll be wrong. And this is actually a name, proper name, Real Madrid, means Royal Madrid. All right. So this is a simple diagram of you have a Chinese speech coming in, have an ASR system which generates n-best list, and our NER system is going to take the hypothesis and extract the name entities. Now, the particular challenge in Chinese NER is as follows. It's more difficult than for English because there are a large number of homonyms in Chinese, especially when we're talking about spoken input. So even for humans, if I tell you my name, 99.9% of the Chinese will not know how to write my name, my Chinese name, right? Because there are many different characters that have the same sound. So that's really difficult. And also, Chinese person names is an open set. So our parents just think of whatever characters they want to put together and give you the name. Now, some people suggest that obviously there are certain bad characters we never use for names, sure. But other than that, anything goes. There is no standard definition of what Chinese words are. So organization names, again, abbreviations, all that. It's I would say there's not a really standard definition. When we see it, we know it, and I can't really tell you the rules exactly.
Excuse me, are you saying, I didn't realize that if you say Fung,
Fung is my family name.
When I say people don't know how to write it.
Fung, people know because there's only one Fung in frequently used family names. But my first name in Chinese is Yan. And let me just, now I've told you, so you will guess which Yan it is. But if I don't tell anybody which Yan it is, their first guess is the wrong one. Usually second one will be wrong, third one they might hit it. So that multiple, so each character, each sound, each syllable will correspond to their on average 20, even 50 characters. So YI, for example, the syllable E has more than 100 characters. That's the sound E. So, then for person names, you don't know the boundaries, and you don't know which character it is. So, of course, the most reliable features of textual NER, such as punctuation, capitalization, well, forget capitalization in Chinese, and syntactic patterns are often not available from voice. So, before I go on talking about how we solve this problem, let's review how we do it on text. Basically, in Chinese, there are two ways of doing NER. One is you just look at them as a string of characters, or look at them as a string of words with segmented, with word boundaries. And in either case, you for character string, you segment them first, and then both sides you do part of speech tagging. And then you can do bracketing, named entity bracketing, and classification in one step. Or you can do a post-classification after you've done bracketing, and then you do post-classification in the second step. All right, and the results are different.
What do you mean by post-classification?
Meaning you just bracket, you just recognize where the boundaries are first. And then the second step, you do labeling, given the boundaries. All right? And the results for these two approaches are actually different. And it's interesting for Chinese. So the basic NER model we use for Chinese is the well-known model, which is the Maxent model for NER. It's the best, so far the best NER model for Chinese textual texts. So I'm not going to go through the detail of the Maxent model. I want to explain that the features are pretty standard. The standard features we use are the target word and context words, part of speech tags, of the surrounding words, of the word itself, so on and so forth. So pretty standard features. We learned that from, we trained this NER model from label annotated data. Now, we have done experiments, and also our center, other people have done more different experiments comparing different models for Chinese NER. And Maxent seems to be working the best. Other than combined models, this is the best model so far. So again, before I tell you our system, these are the experimental setup. The annotated text database we use are from People's Daily Newspaper, and then we have some training and testing data that we use in-domain data, which comes from broadcast news, right? Because this is more like spoken language data. And then our development testing data, we use the MBEST list from the ASR output of BBN system. And these are, again, news and 1,000 sentences and so on and so forth. Right? The MBEST hypothesis ranges from 1 to more than 300, depending on which sentence it is. And this is an example of MBEST output. Well, I guess for this audience, everybody knows what an MBEST output is. Here I want to point out, if you see here, right, you can see these are the same. Okay, I just want to focus on where they're different. This is shi, a character which means especially is. Okay, the is. But here, recognized as some kind of a proper name, right? Because it sounds the same. So, and this is Qin Shi Huang, is the Emperor Qin, Qin Shi Huang.
Let me ask you a question. The NBEST output looks like it's already segmented. Is that?
Of course, it's from the recognize. Yeah, it's a word-based recognizer with word-based language models. Otherwise, it will be very bad. So, as an example, right, this is a proper name here, but because you have something like this, which is also a proper name, it's very easy to consider this as a proper name or location name or whatever. So, this is the problem. What else? Recognition error here. This is a organization, okay, and because of the acoustic errors, phonetic errors, it means different things. And nevertheless, we want to use the MBEST hypothesis and extract the proper named entities. And now we have done some comparison experiments comparing NER on speech data and on ASR output and on text data. And you can see that these are the NER performances for person name, location, and organization. And you see that for person name, the precision drops dramatically because of the recognition error. For location, somewhat less. Organization is also very bad. Right, so these are.
What are the two lines you saying? Drops?
Drops.
There's newspaper text, and what is?
This is one best ASR hypothesis.
Oh, I'm sorry. The first is from text. And
from text is from
speech.
speech recognition results.
Yes,
yeah.
okay.
Another clarification question. You say newspaper text. Are you suggesting this is not the reference transcription of this ASR segment? I mean, you could have done an experiment where you simply had the reference transcription there, right? Instead of...
You're correct.
Because what I'm wondering is whether...
We actually have done that. Yeah. You're thinking whether it's because it's different domain.
Or just different rate or balance of...
Yeah, we actually have done lots of those experiments. I don't know whether this is a typo, but the performance difference is like this.
Yeah, no, I believe it's different, but I would be...
And is your hypothesis that the person is so bad because there are too many persons, while location, there is a limited number of locations which you have in the vocabulary, and so... Is that...
Yes. Because there are multiple reasons. Person names is open set, and the organization names is more open set. Location, the place names, the province names, and university names is more limited. Also, one question is you might ask is, maybe your NER system is not that good. So we compare to the IBM, the best known system at the time, the IBM HMM model, and we can say the performance of our NER system on Chinese is comparable. Okay, another experiment shown that, interesting enough, if we take the speech recognition output and follow the segmentation of the recognizer, that's not as good as if we just throw away the segmentation and just do everything again from scratch, assuming character strings. And the post-classification, as I explained before, is you bracket, you locate where the boundaries of named entities are first, and then you classify them into one of the types of named entities. And in this case, you might not see the graph very clearly, but in this case, in general, the two-step algorithm works better. Post-classification gives a better performance. So the solid lines are the post-classification performances, and the dotted lines are the one-pass performance. So if you will look at precision, then the post-classification work better than the one-step. For organization location, for person name, it doesn't seem to make too much difference.
That's the number.
What's the x-axis?
What's the x-axis? What's 100 what?
This is a hypothesis. The old hypothesis.
I'm sorry.
When
there are hundreds...
No.
Some kind of threshold that you...
No. This is hypothesis. There are some sentences with lots of hypotheses.
Maybe it's the percent of hypothesis.
Yeah, that's possible too. Yeah, we use all the embeds and we use first. They shouldn't drop. I'll check my data. So what we were interested in is the comparison of this line and this line. And for F measure, I'm more concerned with precision. And basically, this tells me that, okay, post-classification work better, but for person names, still doesn't do much. Right? I mean, post-classification or not, person name is still very bad. It's still very hard to recognize. So here is again the MBES output. So we want to use the MBES output to improve NER accuracy. So one way is just to do a simple voting and see if all the hypotheses, so if most hypotheses have recognized a certain named entities, then we accept that. Another way is actually to use different scores, such as the acoustic language model, number of words, phones, number of silences, or NER score, and use a development set and use them as a confidence measure. All right, and you threw all that into a Powell's optimization algorithm, and you optimize. We try optimizing for two things. One is to optimize for word error rate, and the other is to optimize for named entity recognition accuracy. So this is a confidence measure. So let me explain the formula here. Here, this is the SK is one of the 6 different scores, and omega k is the weight for that score. and the total weight is the sum of that. So we have to estimate this omega k with the optimization algorithm using development set. Afterwards, we also normalize the confidence measure, all right, by all the hypotheses. And finally, we have a threshold, which we also found from the development set. We calculated from the development set, and we give a score to we give them confidence measure score to each NER we have recognized. So this seemed to work better than anything else. After much ado, one thing I have to say is that we're still very far from the upper bound. These are the results from the reference sentence, to answer your question. These are the results from the reference sentence for person names, location, organization. And then this is just using the one best hypothesis.
So what's P? P is precision or P is?
P is precision.
So
F is F
so
measure.
it's F measure and precision.
There's recall, but I'm just showing P and F measure, yes.
Yeah, okay.
Okay. So what we can see is that using all scores gives us better performance on person names. This is, on average better. You have some improvement on person names, the best performance on location, and pretty good performance on organization. So organization is, we got it to be, especially in this case, very close to the reference. So we've made some improvement from one best, but overall it's just after we've done all that, it's the results are, well, there's still work to be done.
Let me ask you a question. So the overall error rate of this ASR system you mentioned was some 7%. Can you break down the error rate? So if you looked at only the person names or only the location names?
Okay, we could bring down the error rate if we evaluate person names by the syllables only. In other words, we can actually locate the correct boundary of person names despite the recognition error.
Okay.
All right, and if we don't care what that person, if that's the correct character or not, we just look at it as syllables, which is still useful for speech translation, then the error rates can be brought up a little bit.
Okay. No, I wasn't even going that far. What I was thinking is just comparing the reference transcription versus, let's say, the one best baseline, right? So you have an overall word error rate number, but if I just focused on the words in the reference transcription which correspond to a person name, of those words, how many did I get right? So if your overall error rate is 7%, but your error rate on person names is 50%, then I know that my named entity recognition on that is not going to be all that.
I don't think it's 50%. I think it's something like 30%.
Yeah, no, I know. I'm saying if you could break it down by the three. I'm wondering whether, for example, location is great because you almost always get it right anyway. So, so if you could put a line, one of the lines right there, the reference would be.
Yeah, we have all that data. I can put it in. Yeah. So, but I still think there are things we can do with person name despite the errors. Yeah, still, and we'll continue working on that. So this was our Wanako 2004 paper. At the time, it was the first known result for name entity recognition from spoken Chinese, and it was interesting to see the comparison to English and to text. And post-classification can improve name entity recognition. Resegmentation is better. Weighted voting, passing through the optimizer using development set, also give us some improvement. I'm just say something. We try to optimize for word error rate, and also we try to optimize for name entity recognition. That seems to be the logical thing to do. I don't know, because I was just talking to one of your students about machine translation confidence measure, which made me think of, if you want to optimize for bring the best hypothesis up and that kind of thing. Maybe we could also try those things. So next I want to talk about our work on translation disambiguation. In particular, so I've been doing translation disambiguation for a number of years now. And in particular today I want to talk about the question of whether we can use frame semantics. If you're familiar with the term, it's, you've heard of FrameNet. Or in general terms, it's basically all these kind of ontology, semantic networks. Can those things be useful to translation disambiguation? So previous work, including our own, is usually when we have an input query and want to disambiguate some of the translation candidates, we usually do it like this. We start with dictionary glossing and then using the context to do some kind of a translation disambiguation, similar to word sense disambiguation methods. So previous work, including our own, all sort of use the context model. And in the literature, in the linguistic literature, this is referred to as lexical neighborhood. You're looking at the neighbors of the words you're trying to translate. And today I will talk about another way of doing translation disambiguation by looking at lexical access. Meaning, besides the dictionary, I want to use a bilingual ontology, a semantic dictionary, to do some kind of semantic processing, and I want to give better translation candidates here already. Then afterwards, we can combine this with the context processing, context-based models for better translation disambiguation. So what I'm talking now is the pink part. So first we need to get this bilingual ontology or the bilingual semantic dictionary. And we want to obtain that automatically. You cannot find them in the market or just download them. So the motivation for generating such a bilingual ontology automatically includes also to identify and quantify certain mapping between semantic structures across language pairs. Personally, there's another thing that interests me in this topic, which is that there's a lot of psycholinguistic literature on bilingual speakers. And people argue about whether multilingual speakers like us, we actually have one semantic map and multiple lexicons attached to it, or whether we have separate, independent semantic maps and one for each language. That's a fascinating topic for me. And this work here is sort of a simulation of a bilingual speaker who has one semantic map with different lexicon attached to it, or word senses attached to it. And this is one school of the thoughts in psycholinguistics. And so there's some previous psycholinguistic work done in this as well. Another interest to do this is, of course, frame semantic representation or other kind of prop band representation. They are task independent and hopefully therefore trainable from corpus. So for machine translation systems or speech translation systems, this will be very useful if we can train these semantic structures. And last but not least, as I mentioned, is we want to use frame semantics to improve translation disambiguation. So first, let me show you a frame semantics representation. This is from FrameNet, English FrameNet. You can think of it as the organization of the concepts in the world, right? All the concepts in the world are divided into domains, and under the domains there will be different frames, semantic frames. Here's an example frame called judgment under the domain cognition, and for any sentences that are found to be in the frame judgment frame, it will contain one or multiple of judge, evaluee, reason, and role. So this in FrameNet, each frame also has a lexical entries. So this is kind of like a semantic dictionary, a monolingual dictionary. So under this frame, here are these words which belong to this semantic frame. All these words have part of speech tags because different part of speech tags of the same word might belong to different frames, right? Book.v, I want to book a fly, is obviously a different sense from book.n, a book I'm reading. So these lexical entries are for the frame or for the single frame judgment. And also in FrameNet, each frame contains multiple example sentences that are bracketed and tagged into with semantic rows. For example, here, she blames the government for failing to do enough to help. It's bracketed and labeled as she as judge, the government as evaluee, for failing to do enough to help as the reason, and blames is the predicate. So this is what you have in FrameNet. It's an existing resource. So we want to generate basically a bilingual FrameNet.
How complex can these sentences be? I mean, this is a relatively simple sentence.
Oh, they have complicated sentences, really long ones. They're randomly.
And you can then really classify it only with these four. I don't know what to call it. Frame elements.
Well, each frame has different frame elements. So judgment frame will contain these four frame elements. Another frame will have different kinds of frame elements. And these are done manually by people.
Okay, but I can imagine a much longer sentence
Sure,
with the
sure.
word blames.
Sure.
And the word blames makes it, it's the verb that makes it a judgment frame.
Yeah,
right?
the predicate, yes.
Well, so, I mean, this can be very complex, right? And
There are example sentences that are very long, but because
but
these are...
I'm trying to say that it may be very complex, and then it can't be broken up into elements tagged by either judge, evaluate, reason, or role.
If they belong to that frame, they will have either well, they obviously have the predicate. Sometimes they don't have the role. Sometimes they don't have the reason. Sometimes they don't have the value. Yeah, I can show online.
Okay.
Yeah. Are you thinking about one sentence that might belong to multiple frames?
Yes, that's right.
Okay, that's a very good question. We actually did a analysis of the data. So far, for example, even of this, the workshop output, the empty output hypothesis, we just look at it. I just look at it. So far, it's pretty much one sentence is the verb is one frame.
Oh, really?
Yeah, one frame. That's really important for us to, for us to be able to use this information to help. So basically, you're saying one frame means when I say one sentence, I only have one meaning. Okay. Okay, maybe one word can be ambiguous, but the whole sentence cannot be. Unless you're doing Chinese poetry. All right. Yes?
And just to be pedantic, like, I mean, when you say sentence, you mean like a large fraction or clause. I mean, you could have, this thing, comma, and
Yeah.
someone else,
Yeah. If you have and if you're telling a story and you separate that by comma.
What if the sentence is, she blames the government for failing to do enough to help because she's a Democrat?
So that would just
Because she's a Democrat will be part of the reason.
But then failing
because she is a
to do enough help is not the reason. The reason is that she's a Democrat.
so that would
She's
be
blaming them this way, but the reason is because she's a Democrat.
No, that's not
The
how
term
it's
reason
defined.
might not be the perfect name for the role.
Yeah, that's not
But
called
also
reason.
that.
I see.
That's a different role. Yeah, that's not a reason.
Well,
Okay, I
okay.
guess the other question that arises is whether these things can be determined within a sentence or whether you have to go outside the sentence to determine the roles.
So far, if we look at the newspaper machine translation output, it's pretty clear. Every sentence you try to translate belongs to one frame. The frame might not exist in FrameNet. It's the coverage problem, but it's pretty clear. Sometimes it's not necessarily a verb. The predicate is not necessarily a verb. It doesn't have to be a verb. Yeah.
I'm wondering whether, well, okay, we'll do this one.
All right, so what we propose to do is, okay, we're going to take advantage of existing resource of a Chinese HowNet. You don't have to use HowNet. You can use other Chinese resources to generate bilingual ontology. What's a bilingual ontology? So this is the original FrameNet. It has one under the domain connection, you have multiple frames. Under the frame judgment, you have these lexical entries. What I've shown you before. So what we want to do is to attach to this frame, to each one of this frame, the lexical entries in Chinese. Not just the characters, but also they're part of speech tag, and also they are categories in HowNet. So why HowNet? HowNet is an ontology that's readily available. You can use other Chinese resources if that's available to you. So this will be our bilingual ontology, like a semantic dictionary. So how we generate that? We generate that based on two assumptions. One is that the frames, English frames and Chinese categories with a large number of translated words should map to each other. And the other is that lexical entries if their parent categories and frames are aligned, then the lexical entries should translate to each other. So this is sort of two assumptions we're based on. Using a simple example, so suppose I have this frame cause harm in English. Suppose this frame only has two lexical entries, beat.v and strike.v. So the first thing we can do is to translate them through a bilingual dictionary, just the lexeme beat to da, strike to cui. Suppose each one has only one translation. And then we look up in HowNet, we found that the Chinese word da belongs to two, in this case, suppose it belongs to two HowNet categories, da beat and jiaowang associate. We also look up cui, it belongs to only the category da beat. In this case, we sort of vote and drop the jiaowang associate. And then we align, in this case, we have aligned the cause harm frame to the da beat category in HowNet. And all the lexical entries under the da beat category in HowNet will now be mapped to, not all of them, all of them that are translations of the lexical entries under this frame will be now aligned. So that's the basic idea. We do this with the EM algorithm. We have an initial alignment based on bilingual dictionary, and then we iterate. Right. I think I'm going to skip the detail of the EM algorithm. And this is the result of our word sense dictionary. Some of the examples, for example, the tie, the English word tie has multiple meanings. In this case, tie as in clothing is translated to qing as in the tie in the classical Chinese. And then tie as in cause confinement is translating to 拘束 .v in the restraint category. And then tie as in cognitive connection, as in I have a tie, strong tie with him, is translating to 连接 in the connect category in Chinese. Correctly, of course, I'm only showing you the correct ones. These tie, make, row, feel are some of the most ambiguous lexical entries in FrameNet. So you can take a look at these nice examples, and they align to seem to align pretty well.
Can you say more about the granularity of these categories?
I will. So let me. Okay, so first of all, FrameNet and HowNet they were built separately. They have nothing to do with each other. And there's a monolingual speaker here and monolingual speaker there. So FrameNet, the number of frames in FrameNet and the number of categories in HowNet do not correspond to each other. And the granularity, so there are one-to-many and many-to-one mappings all over the places.
In part, it seems very general.
Yes, yes. But this case, yes, it is. There are many, yes, certainly. And there's some other things like numbers or whatever. HowNet has some kind of a pretty general categories. FrameNet there's more frames than categories, right? Now, what I want to show you is these histograms. What's this histogram? This is showing how many HowNet categories are aligned to each English frames. So this is a histogram. So here I'm saying, English frame is aligned to 0 HowNet, to 50, to 100, to 150, to 400.
Again, what are you doing?
One English frame is aligned to 50, 100, 150, 200, 250, 300, and so on, so HowNet categories. And how many English frames have this many HowNet categories?
Yeah.
Okay? So in this case, we just use a dictionary. We have no, at the beginning, we just translate all the lexical entries by a dictionary. and then map all the categories that contain those translations. Then most of the English frames have, you can see that there are lots of English frames that have, you know, aligned to a lot of Haona categories. It's in the order of 50, 100, 150. And the most is, 350, 360. So that's before EM. After EM, you see then we have from 5, 10, 15, and the maximum number is 30 something. Okay? And so we have reduced the mapping one-to-many mappings, clean them up. So this is after convergence. But still, yes, there are. So the average English frame is mapped to, I don't know, maybe 15 categories. Now, we also have look at the translation accuracies of 11 most ambiguous words in FrameNet. This is the word sense mapping. So we look up the results of the mapping in the bilingual FrameNet. We look up the results of these 11 most ambiguous words: tie, make, roll, feel, and the precision is pretty good. On average, is 82%. It does.
They are ambiguous relative to Chinese, or they are
No, they're ambiguous in FrameNet. So they have the most number of.
They have memberships in most of the
frames. Yes, they have
in
memberships.
the frame lists.
Yes, yes.
Can you define sense translation accuracy?
Oh, it's just what I showed you before. The examples. You look at this. Are they correct or not?
Okay, thanks.
Oops. So it does really well for, I don't know why, but for make it does really well. And this is, of course, with respect to Chinese. Huh? So I'm sure these numbers will be different if we're doing it for French English. Right? For, it doesn't do very well. It does, for roll, it has a particular problem because there's no translation of the word roll in the sense of a bread, piece of roll as bread. In Chinese. We don't have that in dictionary, so we never translated that, so it's never there. What else? Oh, referring to David's question, for example, the word look. English FrameNet divides that into a lot of different looks, like appearance, emotion, I give you a look, and Chinese has fewer categories. So a lot of this, we don't consider that correct if it doesn't really disambiguate between two senses that actually exist in FrameNet. So I'm not going to get into the argument of why should we follow FrameNet instead of following HoNet. But so from the FrameNet point of view, these are the accuracies of the 11 most ambiguous words. So these are the number of frames and senses in FrameNet for each of this word. So tie belongs to 8 frames, look belongs to 5 frames. So we can say they have at least 8 senses or they have at least 5 senses. Right. So next we want to do experiment of using this system, using this result of bilingual ontology. Can we use that to improve translation disambiguation? Can we pick out the better translation candidate from a bunch of them? So here is an experiment where we use the example sentences in FrameNet. As I mentioned, FrameNet the coverage is a problem. They don't have all the frames in the world, and they don't contain all the words in the world either. So for our experiment, we just want to evaluate on the sentences that are in the FrameNet, so they definitely exist. They definitely have the frames there. So for example, in the sentence under South African law, I'm not going to read it. There's a word hold, the man. The police could hold the man for questioning for up to 48 hours before seeking the permission of magistrates for an extension. To answer your question, so this frame, they're only concerned about hold frame. Right, before seeking the permission is just like accessories there. Okay, so this sentence, the The first step is just to find all the translation candidates for the word hold. And there are lots of them. I'm skipping a lot of them. I just have here. So I skip. So there are a lot of translations, and each of these for example,
This is
na.
in a regular Chinese dictionary.
Yeah.
You would find all this in the
No, for all this I will find in the regular Chinese
as
dictionary.
a translation of the English word hold.
Hold, right. And then I have na as in this category. Then I look this up in HowNet.
Yes.
Okay, because na can belong to this category, this category. Each one of these belongs to different categories. So now I have the so-called HowNet word census. Now I want to pick out the correct translation. So I go back to my bilingual ontology and I pick out the one that's in the bilingual ontology because I know that hold detaining is aligned to ko-liu in detain. Hold detaining is not aligned to anything else. Okay, so this is a very good example, right? Most cases, there will be several pluses and lots of minuses. So then we evaluate this over randomly selected frame sentences, just exist there. And we evaluate the precision of recall. So positive translations by our method is marked by ++ sign and it's counted, A. Negative translations are B. And then the human evaluators will give you the true translations, which is A, yes, and B, yes. And erroneous translations as in A, no, and B, no. So the precision is then counted as A, yes, divided by A, which is around 75%. If we just use dictionary glossing, we get 15.8%, very low. Recall is around 76%. So we're very, very encouraged by this result. And actually, when I first look at the bilingual FrameNet word sense mapping, I was very happy already because we see that the precision there is very good for the ambiguous word senses. So this is the first empirical result showing that we actually can use frame semantics to help translation disambiguation. And we think that it will complement the context-based methods. A lot of the word sense disambiguation methods, they look at the context of the words. And there's a great potential for us to use frame semantics to help SMT, statistical MT, cross-lingual IR, etc. As I mentioned to you before, when I look at the SMT output and best hypothesis, manually I could tell that each of the sentences would correspond to one frame. And if we can use some of these methods correctly to re-rank the hypothesis, maybe we can do something better. So the last topic I'm going to cover is the accent modeling, dealing with confusions in accented speech. This is a work that's, you can say, a continuation of the work we did here in 2000, summer workshop, when we were dealing with spontaneous speech in Mandarin speech. And here we are looking at specifically at accents, or not standard Mandarin speakers, but accented speakers. Mandarin speech is, there are about, well, depending on the linguists, there are about 7 to 11 different dialectal regions in China. Most of us do not come from the standard Putonghua region. And we speak Mandarin fluently, not since birth, since very young. But all of us have some kind of accent. And we can usually tell which accent you have and I have and so on and so forth. Now, so that's a kind of similar, almost similar to recognizing English by people from people who speak it from all over the world, right? So in our case, we focus on in our experiments, we have so far experimented on Cantonese accented data because Cantonese accent is, it's quite strong. And we're in Hong Kong, where, the Hong Kong people speak Mandarin with a strong Cantonese accent. We have the data. Now, Cantonese regarded by many linguists as a distinctive language from Putonghua or Mandarin. Syntax is different, lexicon is different. Pronunciations are different in 60% of the cases. So I think of French and English in terms of pronunciation. The same word, you pronounce it differently. So we suggests that in accented speech, there are two kinds of confusion. Well, accented speech is speech recognition, right? We're looking at this from speech recognition point of view. Now, there are phonetic and acoustic confusion, and they're different. We're suggesting that we need to distinguish these two confusions, and we'll need to model that differently. What do I mean by that? First of all, suppose we have three base form models trained from Standard Mandarin: the base form model for D, the base form model for J, and the base form model for Sh. All right, in Standard Mandarin. Now, the model is very different from the other two, whereas these two are kind of confusable inherently, has some acoustic confusion already. Now, I have an accented speaker who tried to pronounce, this guy is trying to pronounce zh, okay, the pink sound. That's the intention. So there are three different cases that could happen. One is this guy just doesn't know how to pronounce, oh, this guy pronounces very well, and it's recognized as zh correctly, so there's no error. Second case is he or she pronounces it as something like d, and it's recognized as d, right? So in this case, we say there's a high phonetic confusion with low acoustic confusion. It's not the fault of acoustic distances between the models, it's because the guy pronounced it like the other phone, right? And there's a third case where the guy pronounced zh somehow between zh and sh, somewhere there. So then we're gonna, so there's a chance that it will be recognized correctly, or it can be recognized as the other one. In this case, we have both phonetic confusion and acoustic confusion. So some methods people have tried before to deal with this accented speech is that, okay, we're just gonna create some kind of special Fung set, Fung units. We can create a Fung unit called zh underscore d, and train that with the samples of this accented speech. And we can also create the zh underscore sh. Sorry, this is a typo. This is a sh. And then we do the same. Now, the problem with this is that because this is already acoustic confusable, this is yet a third acoustic confusable unit. If you have this extended unit and you put it in the multiple pronunciation dictionary, you're just gonna make lots of errors anyways. So it won't help. So we don't want to do this, all right? So what we want to do is, for that kind of confusion, we do something. For this kind of confusion, we propose another method. So this is what we suggest. First, we detect whether there's phonetic confusion or not in the accented speech. All right, and we propose a measure called likelihood ratio test to see whether something is consistently recognized as another phone unit. If not, if there's no phonetic confusion, then there's not going to be any problem for recognition. If yes, then we want to see whether there is acoustic confusion or not. And we propose using the asymmetric acoustic distance measure to do that, to measure it. If there's no acoustic confusion, only phonetic confusion, then we use the Fung set extension method. If there's also acoustic confusion, then we propose using decision tree merge with model reconstruction. This is a likelihood ratio test formula. What we do is basically looking at how often some phone unit is recognized erroneously as another phone unit. And so some people count frequency, but we found that this likelihood ratio test is the best way. It's more reliable to find consistent phonetic confusion pairs, rather than something just because there's a sparse data problem, or there's a, you know. So this way, using this likelihood ratio test, then we extract a whole bunch of phonetically confusable pairs in Cantonese accented Mandarin. These are some of the examples we extracted, I think. Originally, there's more than 6,500 confusable pairs. Using this test, we extracted around 80 pairs. And then we use the asymmetric acoustic distance measure. This is basically measuring the model of one phone and the other, and its distance, and we measure it in the asymmetric way, because we reason that when the speaker is intending to speak zh, and it came out as d, is different from when the speaker is intending to speak d and came out as zh. right? One might happen, the other might not. So it's not symmetric. Right. So from that we can distinguish between two kinds. One is high phonetic confusion, low acoustic confusion unit pairs. The other is high phonetic confusion and high acoustic confusion unit pairs. So for the first kind, we just use extended Fung unit and create, augment the pronouncing dictionary with the additional Fung units. Because for this kind, we're confident that if we have multiple pronunciations, it will not lead to further confusion. For the other kind, these are, from the subset I show you, this is the subset of the subset of the phonetic confusion pairs that also are acoustically confusable. Then what we do, let me just explain with the diagram. This is what we do. We expand the base form tree, decision tree. For example, we have the standard decision tree for the sound yao. Yao is a final in Mandarin. And this is the state 3 of yao, right, of the standard decision tree. Now I create the auxiliary decision tree for the unit, the third state of yao recognized as yu. And then there's also another one for yao pronounced as, recognized as yo. Okay, these are different accents by different people. And then I'm gonna tie the notes, different notes, by measuring the acoustic distance. Okay? Not the asymmetric acoustic distance, this is just acoustic distance. And sort of merge these trees, create a big tree. So now this big tree contains information about the standard Mandarin sound and also the different accents. And then if you walk down the tree, if you have a standard, if you pronounce it correctly, it walks down one way. You pronounce it with one accent, walks down the other way. With another accent, walks down the other way. Right, that's the idea.
Do you know accent beforehand? I mean, do you know that the speaker has a particular accent before a particular test speaker?
Test speaker development, we know. We're using Cantonese accented data.
Right, to walk down.
When the test speaker, we don't know. We don't know. It could be a standard speaker, standard speech speaker, or accented speaker. So the idea is we need to improve the recognition rate on the accented speaker's speech without causing degradation on the standard speaker's speech.
So you could walk down, to walk down different paths, you need that information at one of the nodes, right?
I don't need the supervised information, no.
Let me understand. I think I understood you to say that you have, let's say, the standard Mandarin speakers, and then you have, let's say, people who pronounce yao as yu, and another set of people who pronounce yao as ya, or whatever the other sound is. And so you build 3 sets of Gaussian mixture models for that state. One by going down this tree, one by going down that tree, and the third one. During recognition time, you're going to use a big mixture of all 3.
Yeah, we use a mixture of all trees.
So
yeah.
That's why at test time you don't need to know. So it's like
So
merging mixtures.
You're not going down different paths. You're basically taking a mixture of all paths.
Yeah.
I understood you to say that you were going down.
No, you go down 3
You
different
do
trees and merge the
different
Gaussians.
paths because it
But
will,
you take a mixture of all the paths. You're not
Not always that.
choosing.
not the paths.
I mean, all the different accented paths.
How do I put this? So it's exactly what this picture is showing. So for this, it will have a mixture with this, right? For this note, we'll have a mixture with that. So after it's merged, then this has a mixture with different accents. But if you have accent, then it might walk down, how do I put this? Well, you still have different paths, right? You will have different probabilities of going down different paths for that one sound. You still have different paths. But each leaf node is a mixture.
We could do this offline.
But just let me ask one more question then. So to build these 3 different trees, do you read data with accent labels, or do you create that from the phone, from the transcriptions? Like you
So we created from those phone units with high acoustic confusion and high phonetic confusion.
But to measure phonetic confusion, do you have reference labels that tell you what the exact phones are?
So some data is carefully transcribed in the phone level, is that so?
Yes. Well, it's standard transcription.
Okay.
Okay, so the first step, okay, let me go back. How do we get 6,500 those pairs? It's by phone recognition.
Oh, by phone recognition.
Yeah. And then we have to do likelihood ratio test to make sure it's not recognizer error, phone recognition error.
So you do phone recognition and then you assume that that is the phone transcription. You don't worry that it's automatic. And then you just use that to decide, for example, the yao going to you.
No. After that, no. After that step, I have to do the likelihood ratio test. Right. And we actually look at those pairs and we compare to some linguistic rules, and they're pretty good.
Right.
Of course, depending on the likelihood ratio test threshold, you might get slightly different pairs. Well, that's engineering concern then. How many pairs do you want? And it's not going to be.
Okay, let me make one more attempt to clarify. So let's say that there was a reference transcription in which the phoneme was supposed to be yao, and your phone recognizer said it's you. And then in all these tests you decided that this is a phone confusion of the kind where it is both acoustically and phonetically confusable.
No. We first decided this is phonetically confusable, obviously.
Okay. Yeah.
And then afterwards we have to look at the model of yao and you. Yeah, to see what it is.
It's also acoustically confusable.
Yes.
So that instance of yao is
you.
going to go into the building of the first tree.
Right, auxiliary tree.
And
exactly.
some other instance of yao may go into the construction
Different
of the third,
auxiliary
and yet
trees.
others
Yes.
will go into the construction.
Yes, exactly. And then you merge them together into a big tree.
One more quick question.
Yes.
So how good is the phonetic simple phone loop recognizer? Do you have numbers for that?
How good is the standard speech?
Yeah. I mean, the one that you assume as the reference up to you.
Like you have a phone recognition accuracy on some data which is manually.
I want to say it's about 70% syllable accuracy. I have some data. I'll go to that table. Okay. So here, so we have training data from 100 standard Mandarin speakers, and then development data from 20 Cantonese accented speakers, and test data from 9 accented speakers and 9 Putonghua speakers. So for speaker-independent speech recognition, you have to use one system for both. All right. So we need to see how it does for the accented speakers as well as the standard speakers. So their previous accent adaptation methods then will adapt the model to a particular accent. Then it won't work that well for the standard speech anymore. So that's not what we want. We want it to perform better for accented speakers and also works well for standard speakers. The recognizer is our own telephony word recognition system, but what we're interested is in the comparison of different methods. This is what I told you. So under the 7980 high phonetic confusion pairs, we got 57 of them as with high acoustic confusions, the other ones with low acoustic confusions. Here is the experiment result. All right, here we go. For accented speech, the baseline word error rate is 20%. For standard Mandarin speech, the baseline word error rate is 7.9%. Huge difference between the two.
What is the task?
Chinese short phrase recognition. So, but we're interested in looking at the difference here and also at the difference as we use different methods to improve it. So, one model we use is just use Gaussian mixture sharing. And on all these phonetic confusable pairs, we just assume everybody has high phonetic confusion. And that gives us 18.2% word error rate and 7 here. So actually, it gives improvement, obviously. Now, if we also use the multiple pronunciation dictionary probabilities, but again, we just assume everybody has high phonetic confusion and without acoustic confusion. So because of the multiple pronunciation dictionary with probabilities, it gives an even better performance than the previous one. Although for Mandarin speech, somehow the performance decreased a little bit. Somewhat, actually quite a bit. Now, this is a method where basically we do this decision tree merging thing for everybody. So assuming everybody has high acoustic confusion. Now that gives us better results than the previous methods, right? Actually, it's better than all previous methods. And then the method I just presented, which is to model them phonetic confusion pairs and acoustic confusion separately, gives the best performance. Yes.
Two questions. Are all these numbers significant, and comparison with maximum likelihood linear regression adaptation or something like that?
They are.
Speaker adaptation?
They are. We did a lot of experiments comparing those, and they are in the paper we're working on right now. A paper that's in revision. This is just one of the comparisons. So what I want to try to highlight is that you do have to separate them, these different units, and then you will get better performance. To summarize, we suggest that accent to speech contain both phonetic and acoustic confusions. We need to differentiate between them and model them differently to give the best performance. So those were the projects that are related to speech translation. And there are other ongoing projects in my group right now, and I mentioned a few that I would like to mention here. One is the continued work for the translation disambiguation. We're building a bilingual semantic parser for MT and CLIR applications. We've been continuing our work on mining bilingual sentences, mining bilingual paraphrases, mining lexical translations from quasi-comparable corpora, very non-parallel corpora. We're working on multi-document, multilingual spoken language summarization. So not all in one, not multi-document and multilingual and spoken language. We're doing spoken language summarization, we're doing multilingual summarization, we're doing multi-document summarization. Why are we doing that? We're basically using one framework for these different kinds of summarizations. And another separate project, which is sort of unrelated to most of this, is embedded speech recognition. We have projects on handheld device speech recognition. We're going to start a project on automobile speech recognition, working with industries. So that's my introduction of that work.
Questions?
Yeah, I remember the HOMNet has both Chinese sense and English sense in it.
Chinese sense, no.
For each word, it has both the category in Chinese and the category in English.
No, it's a Chinese category. It just has an English name as well.
Okay, so,
Right.
so do you in any case use that
No.
information?
We use the HOMNet lexicon, meaning for each Chinese word, it has also English translation. We use that as part of the bilingual lexicon. But the HOMNet category, for example, da, beat, it just calls the da category beat. But this beat doesn't have anything to do with a beat. There's no beat frame in FrameNet. You know what I mean? It's just a tag. It's just.
So it's just an English name.
For the da category. Yeah. Sometimes the category name is the same as the lexical entry name in HOMNet as well. So for example, da would belong to the da category. But,
So you don't think that's built by assuming already some kind of bilingual information rules?
if there's any, it's just kind of lexical translation only. It's not any sense.
Okay, this is kind of low level.
Yeah. I mean, the HOMNet people are not thinking of English senses. It's not their job. They're monolingual. You can think of it as a monolingual Chinese speaker, monolingual English speaker, and we try to teach them to speak to each other. Yes.
Going back to the top level slide that you had about adding ASR and then NT. So do you actually take advantage of the N-best that you get out of ASR to improve your NT, or you simply use the one best from the ASR?
Right. We're trying. So we use the N-best from ASR to improve NER. All right. and that forms part of the semantic structure. We do not use the n-best from ASR to improve the n-best of MT. It's challenging for now. So for improving MTs, we're focusing on how we can use semantic information to re-rank the n-best.
Yeah, just going back to your last section, do you think separately trying to classify the accent of the speaker would be possible? Would that help you? So you don't have a separate phase where you like classify this person as a Cantonese accent?
No. Okay, in theory, I think we think that the method we propose can be applied to multiple accents. In other words, the speaker-independent system. We can basically build different auxiliary trees for different accents. Cantonese accent, Shanghai accent, this accent, or merge them, have a mixture model for the tree, base form trees. And then Cantonese accent speaker and Shanghainese accent speaker in the test set it would do well for all of them. In theory, in principle, it shouldn't
Although
be a
such model
problem.
doesn't know that the speaker is going to have the same accent on phoneme number 2 as they did on phoneme number 1.
No. Oh, exactly. No accent context. No.
Right.
No. So in other words, I don't even assume that I'm going to have a consistent Cantonese accent in one sentence. Right? I might speak halfway,
Yeah.
I have a Cantonese accent, and part of that I speak quite well. Because, different Cantonese accent speakers have different degree of fluency in Mandarin, just like anybody. Somebody's accent is, we might have the same accent group, but my accent is stronger than his. Right? And so certain phones, I might have a stronger accent than them.
I can see how you could do that, but it's not necessary. But just kind of thinking along those lines, you might even find out that if somebody is speaking Mandarin with a Cantonese accent, they don't know like unusual words, so you could actually modify.
Change the language.
Yeah, I mean, if I'm speaking Mandarin, you know that there are like 3 words that I could use. So that helps you.
You mean at the lexical level?
Yeah, at the lexical
certainly,
level, they're not going
certainly.
to use some obscure kind of complicated, archaic words.
Well, actually, it's the opposite. The Cantonese will use very archaic words because Cantonese is more archaic than Mandarin as a language.
But the point still holds. You can adapt, even the vocabulary probably based on the accent.
Well, she pointed out that there are degrees of accent, right?
Yeah. Well, depending on your objective, are you trying to classify the accent, or are you trying to?
I have a strong Czech accent, but I don't think you would.
You're an exception.
For my lexicon.
Right, but the norm would be that you would have a different dictionary, or that you would have a different vocabulary. So,
Depends, right? Depends.
Okay, well, let's. So, this is a situation. I don't know whether they want to go to the hotel first. I have my problem because I can't start my car. Right?
Oh, you still can't?